Hello everybody, I'm glad you decided to click on this video, thank you very much. Today I'm going to be showing you how to do this. And no, I'm not talking about the weird character and the simple pixel art platforms he's jumping over, but I'm talking about the lighting system in this scene. It's a 2D line of sight light shaft lighting system in Unity, and the reason I'm making this video is because when spring break came around and I wanted one, I went on YouTube and I went online and I found there was a sphere lack online of people showing how to do this in Unity. There are a few articles and videos of how to do it in other gaming engines and how to do it if you're just doing like straight OpenGL or something like that, but nothing for Unity, which is what I wanted to do. So I made a video based on the information I could find. And I hope that after watching this video, if you find other ways to make this even better, please leave an explanation or even make your own video to help out the community a bit more. So I will admit that the method I used is a little bit more engineering-ish and patchwork than I would like. It doesn't take full advantage of the 2D-ness of the scene, and I don't think it's nearly as optimized as it could be. So again, if you're able to make it better, please let us know in the description below or even making your own video. So I did mention that I watched some videos and read some articles on this before diving into it myself, and you can also find a couple of those in the description below. And I'd especially recommend you reading the quick article on how this works before you dive into this video, just because it might explain the method a bit more for you. So let's go ahead and close out of this demo scene and go into my actual scene that I'm going to be working on. So this is just a simplified version of what you just saw. And if I hit play here, you can see it's really just the same thing except without the light, which is what we're going to be making, obviously. So before I dive into the exact how this works, I want to explain what I've already got set up so that you can follow along if you're someone who likes to follow along. So first of all, there's not much over here um, in the hierarchy. There's basically a main camera, a grid with a tile palette that I threw together, and a character. Now this tile map with the collider connected to it, I'm not going to explain exactly how to set this all up because that's out of scope of the video. There's plenty of videos out there how to use the tile map system in Unity, and there's great videos out there for pixel art if you're interested in that too. So I'm not going to go into that, nor am I going to go into the character animation or the character movement scripts or any of those collider components, because those are for the overall game, and all I'm doing is showing you how to do a 2D lighting system. I will mention though, however, that to make this work, I was not able to use 2D collision. So if I go sideways, you can see that I'm using 3D colliders on all of my objects. Also worth noting that these objects, for this to work, what we're actually going to need is vertice location. So these objects are the shape of their box collider, because in Unity, as far as I can tell from looking around, there's no way to get the vertices of a box collider. You have to get the vertices of an object. To explain why that's important, let me quickly run down how this lighting system works. Now, hopefully you've already at least read the article, but if not, basically, let's say we've got a light right over here, and we want light to be casting around the edges of the object. What we want to do is cast a ray to each vertice in the scene, and then cast a ray slightly to the left and slightly to the right of every vertice, and that'll give us exactly where where the light misses the objects and goes past and hits the wall or just goes past into infinity. And then from that, we can create what's called a triangle fan, which I'm going to explain later on if you don't know what that is, to create a mesh which we can put our light texture on. And we'll just procedurally do that every time an update. Now, I'm also going to mention, I think this is worth mentioning, that if you don't have experience in Unity and you don't have experience in C#, you probably will struggle with this video. But then again, if you're trying to implement your own lighting system, 2D lighting system in your platformer game at this point without that experiment, I highly recommend you watch someone with some introductory videos on Unity. All right, so I'm almost done with the basic setup and explanation, but so that you make sure you've got everything lined up. When you've got your tile map or your world or your sprites in place, then just add these other objects. And these objects are not part of that sprite. So add those to make sure they're really lined up properly. and then deselect the mesh render. Now this is a bit tedious, making sure that all of these objects are in the right place. They can overlap, as you can see right here, and that's perfectly fine. If I were making an actual scene for my game right now, I would take a screenshot of the world, bring that into Blender or another 3D modeling software, and I would create my own mesh to line up perfectly so I can make sure that the collision works on these edges properly. You'll notice that in the finished product that it's not perfect, but this method, this quick and dirty method, is best for the video, and especially if you don't have experience in 3D modeling such as Blender or Maya. I believe that's the majority of explanation I have to give to how this is currently working. So I'm going to dive into actually implementing this light. So first of all, what we're going to want to do is create an empty object, and I'm going to call this light. This will be the object that holds the script and sort of controls how the light works. And how we're going to have it is it's going to be in the location where the light is. So I like to put the light kind of up here at an angle. It gives a good chance to cast light around these different objects, really see if it's working. And then right after creating that object, we're going to create a 3D object, and it can be any one of these basic 3D objects. Basically what we're going for is something that has a mesh filter connected to it. So I'm just going to do a cube. I would recommend you do the same thing because I know this works. Haven't even worried about testing anything like a sphere. They should work. And you'll notice we've got the mesh render right here, and we're going to leave that checked because we want to be able to manipulate the mesh and be able to see it. We are, however, going to remove the box collider from the object, and we're actually going to deactivate the object for right now because we don't need it, and just worry about the light. All right, so let's go ahead and make our script. So I'm going to hit Add Component, and I would type in Demo Light Caster right here. Actually, I'm going to go ahead and do that. As you can see, I've done it a few times, so it's giving the suggestion, but basically you create a new script, call it something like Demo Light Caster or Light Caster, and we're going to create that and go ahead and open it up. Now, because I am a grad student and I am very busy and don't have an entire weekend to throw this together, I'm going to be doing a pretty lame way of explaining how the code works. I always love it when a YouTuber explains exactly each line as they're writing it out, so I can see everything coming in and they don't miss anything. And I always get a little annoyed when people start copying and pasting code and then trying to explain it and missing things and not spending enough time on certain things. However, it is a lot faster. So I'm going to be doing that. I'm going to be copying and pasting code in, and I'm going to do my very best to explain, perhaps at sometimes over-explain, exactly what I've done. So you're going to see me copying and pasting code in here and updating what I've got currently. I apologize for that. That's just the way I can justify making this video. So first of all, I'm going to paste the first bunch of code. And if you've just created this, this script, none of this has changed, none of this has changed. The onStart method is the exact same, and I'm going to leave it there because we're going to use it later. And then the only thing we've changed is this line right here, and we have added this. And so I'm going to explain those pieces. So this public game object, scene objects, this is all of the objects that we want to be interacting with the light, anything that we want the light to consider in the way. So this is going to be all of those objects that we added in that are 3D objects. So I'm going to go ahead and populate that game object, scene objects really quick before I forget. So I'm going to come in here, and then I'm just going to drag all of the objects into the scene objects variable. Now, like I said before, if this was a real scene, it would probably be like 1 or 2 objects that I'd be dragging over here, and they'd just be extremely complex objects that I'd be putting in this list. But the nice thing about this is it means you can make some objects not interact with the light. So if you've got a background or a foreground to your scene, or if you've got the light in the background and you don't want the actual scene to be interacting with it, this is a good way of handling that. Now, on my character, I've also got a couple collider objects connected to him. So I'm going to actually add those to the light source as well, so that when the character moves around, he actually affects where the light is and where the shadow is. So now that we've added that, I just like adding that as soon as possible so that I don't forget about that. We're going to go back into the script and I'm going to explain what's going on in this update method. So first of all, what we've got here is we're just a simplifying thing. So vector myLocation equals this transform.position. We're going to be using the current position of this object a few times, and so I'm just making a shorthand version basically to make the code simpler. The rest of this double for loop, is basically so that we can go through every scene object and then every vertex within each scene object. So as you can see, this first for loop goes through it starts at 0 and then goes through the scene objects.length. So we can loop through all of the scene objects. And then in here, let me make it a little easier. We're just going to do another shorthand like what we did up here. We're going to create this vector3 array called mesh and set it equal to the scene object at this current position, at first the first scene object in the scene, and get the component for the mesh filter and get the vertices in that mesh so that we don't have to keep writing this every time we just really want this. Then when we do that, we go into the inner for loop, and that's going to be the length of this mesh. And so now we're on a specific vertex in a specific game object. And this is where it gets a little bit more complicated. You see, these vertices, yes, it's represented by a vector 3, so an XYZ position, but it is currently in the object's coordinate system. Now, if you've never dealt with like matrix multiplication or sort of 3D graphics, hopefully you've had at least a little experience by the difference between a local and a global coordinate system. So currently these vertices are in the local coordinate system for this specific object. So if it were the vertices of this object, this would be 0, 0 instead of the center of the world. Well, we don't want that because we're not thinking about these different objects individually. We want to know where the vertices are in the entire world. So that's where this comes in. We're not simply just taking the vertice and setting it and casting a ray towards it, but we also have to do this transformation function. And it's set up like this. So basically what this is what we want to store in vertice location, or vertloc, is the mesh, the vertice at this position in the mesh, transformed from the local to the world matrix, the local matrix being the scene objects transform, and the world matrix being the world matrix. And then this is just saying multiply a 3 by a vector by a matrix, basically. So if this is a bit confusing, maybe you haven't dealt really in the lower levels of 3D graphics and matrix multiplication and everything. It's okay if it doesn't make a huge amount of sense. Just really, this is the most interesting part about it. Are we transferring from a local to the world matrix, or are we transforming from the world to the local? Since this is currently in the local system for the scene object, which we don't want it to be, we're transforming it to the world matrix and then storing it in this value, because that's the direction where we want to be shooting that ray. We're going to be doing this a few more times throughout the code. So if this is bugging you, you can go to like Unity's help website and read up on this a bit more. But just know that that's what this is basically what it's doing. So after that, we create a raycast hit, which is what we're going to be passing it into the raycast. Another raycasts are also something you can look up on their website, but it's just like how this works is physics.raycast. The first value is the position where the raycast will be shot from, or the ray shall be cast from. And then this is the direction of the specific vertice. We can get that by simply doing the location of the vertice minus our start location. And that's going to be casting a ray in that direction. We're going to be storing the information of whatever it hits along the way in this out variable hit. And we're going to only cast 100 units. After 100 units, if we don't hit anything, then what we return is the vector 0, 0, 0. And then, because you can't actually see this raycast, we're going to just draw a line. And we're going to draw it between the start location and wherever that raycast hits. And we're going to color it red. So if we save that and come back over here and hit play, we'll notice that it seems to be working pretty well. One second. There we are. It seems to be working pretty well. as in it's going to all of the different points, but didn't we specify that it should like hit into colliders? That's what the raycast should be doing. The reason we're seeing this is because this is not a raycast 2D as it ideally would be. Instead, this is a raycast 3D, and if I come to this light source, you'll notice that our Z is way off when it should really be 0. So if I change that to 0, then you'll notice that it's actually colliding into objects. So it's always a good practice when you're doing this. Maybe click on here and make sure things are actually lining up and colliding properly, and then go back into 2D if your collisions don't seem to be recognizing. So I'm going to go out, change that to 0. That's the light source. And come back in here, and it's working great. We're getting a ray cast to, here, let me click on that, ray cast to every vertex in the scene, and if you see me moving around, those vertices are following me, so it's procedurally happening. However, this isn't ultimately what we want. As I explained early in the video and as those resources in the comment explained, what we really want is not a ray just simply going to each vertex, but we want one slightly going past it. And the way we do that is instead of casting one ray to each vertex, we cast two rays, one slightly to the left and one slightly to the right, so that we know one will definitely collide on edges, on corners, and then one will definitely go by it. And when we say slightly, I basically mean as small a number as you can make without the one going past it accidentally colliding anyway. Now, the tutorials I've seen online actually include three rays, the one that we have currently, and then those two other ones. As I've found doing this, you don't actually need to cast this one ray. You only need to cast one to the right and to the left. And this is extremely beneficial because it actually cuts down most of our computation by a third. So don't worry about doing 3 per vertex. Your total amount of rays should be number of vertices times 2, not times 3. All right, so let's go ahead and try to implement that slight offset. So I'm going to hit pause, and I'm going to come back over into our script, and I'm going to do another copying and pasting. And then I'm going to go ahead and explain what I've changed before it gets too confusing. So up here is all the same thing. This is the first thing that's different. And it's just our offset. So public float offset equals some small number. In my case, I found that this works pretty well. If you get a little bit of jittering along edges when you have this value, try to decrease it as much as you can to avoid any weird effects you see. Too much decrease, well, you'll see bad effects in that direction. I don't really know how to explain them. You'll see what I mean. But I found that this value works really well. Something small, but not too small. And then down here, let's see. The only thing, not much has changed here. All of this is the same. This is the first difference right here. Instead of creating one raycast hit, we're creating 2 of them, called hit and then hit 2. And then down here, we're doing this twice. But you'll notice this line is different than what we had before. So all of this is the same, but instead of the direction being just vert location minus my location, we're creating a vector 2. So we're kind of creating a raycast 2D instead of vector 3. And then we're factoring in that offset. So it's vert loc x minus vert my location x, and then minus offset would be our x value. And then y minus offset. And then we pass it out with the hit value. And then our second raycast for hit 2 is just the same thing except plus offset for both of them. So that's the way we're doing slightly to the right and slightly to the left, is plus and minus offset. This is one of those things that I feel like could be optimized a bit to be a bit more realistically right and to the left, but this works pretty well for me. And then draw just 2 lines, one red and one green for the hit and the hit 2, and let's see what happens. So if I come back over here, let the script compile, and then hit play, we'll notice that it sort of seems to be working, maybe a little bit. So first of all, you may think, okay, that's great. Look, we've got the line casting right by here. And then over here as well, we've got these lines, these rays casting right by. And even better, when I move my character around, you can really see in some positions that it seems to be sort of working a little bit. It casts a little bit around him. But then we also notice some issues, like mainly issues. For instance, it's not working at all over here, and it's not working on this. And we've also got this weird line cutting through the entire scene going to what looks like 0, 0, 0, and it's not reacting to rays at all, or objects at all. So what's with that? These two problems of rays not being cast and a random ray being cast are actually one and the same problem. The issue is there's many of these rays that are actually getting cast, but after 100 units, they're not hitting anything. And so they're returning 0, 0, 0. So all of the rays that should be going past here are actually going to this spot right here. And I can demonstrate that if I create another object, and let's just create a cube, make sure the z value is 0. And then if I move this around, you'll see, okay, so that line actually is being cast there, and same for here. So it is working, but we just need to make sure every ray actually ends up casting against something. So I'm simply going to do that by making the entire place enclosed. This is perfectly reasonable. You're not going to, and you can even leave these objects visible because no one's going to see them. You just push them far enough off the scene. If you've got a really big scene, you push them even farther off the scene, and it's not going to be a problem. Wrong coordinate system. And then I'm just going to put one on the top and one on the bottom. Make sure it's stretching across the entire place. Again, this doesn't have to be very well done. No one's going to be able to see it. They just have to be overlapping. So that's basically what we want to do. And you can see now, if I zoom in, everything's working great. And I can actually move my character around, and we can see that the rays are casting by him as well. Now, let's go ahead and end that, and then put those back in just to make sure that they actually stay in there. And now let's go back to the script. So, well, first of all, I want to go back in there to say what we're going to do next. So great, we've got the lines casting by, and it seems like we're almost done, right? Okay, we've done all the hard work. We know where all these points are. We can just create our triangles, right? Well, there's a few other finicky things we're going to have to do before we're all the way there. But the basic idea that we want to do now is we want to get these points. We need to organize the rays based on the angle that they were cast at, because they're currently just sort of all happening all around the place, so that we know where to draw triangles. So we don't want to draw a triangle between this one and the center. We want to do one here, we want to do one here, we want to do one like here, and so on and so forth. So we're going to have to sort things and make sure everything's in order. We're also going to have to deal with the UVs, but I'll show that in a bit. So first of all, before I dive into the code, I want to make sure that these objects themselves are included in our scene objects to be activated on. So that, I think this is just a good practice, just to make sure that the light's just working nicely. And so now you see we've got a few more rays that we're casting, but it's honestly not that many. All right, so let's go back into the code, and this is going to be a lot that I'm copying. So don't freak out, please. I'm going to explain it very slowly. Perhaps too slowly, but err on the side of too slow. So first of all of this is the same. Here's the first section that's new. This public game object's light rays, this is going to be the object for whose mesh we want to manipulate. So if I come back in here, the light, once it compiles, the light, I want to reactivate this. This object is going to be what we're manipulating. And like I said, we didn't want to deactivate the mesh render or the cube filter because it's actually what we're going to be printing to the screen. So right now it looks like a block, but it's going to look good when we're playing it. So before I forget, I'm just going to drag this over to the light rays, drop it in there, and go back in here. So that's what the light rays are. And the mesh, this private mesh, is just what we're going to be storing, what we're actually going to be manipulating. So if I come down here, skip this line for a second, and go into the start, you'll notice that this mesh variable is set to the mesh of this game object, lightrays.component mesh filter. mesh. And again, that's just shorthand, so we don't have to keep writing this over and over again. We can just refer to this variable. The next line is a struct or a structure. Now, it's definitely very possible you've never dealt with a structure before, but it's pretty simple. It's almost like a very basic object. So you can almost think of this as like the object, and then there's three variables in it. It's different, but I'm not going to worry about how this works in great depth. This is basically so that we can have an angle and a UV go for every vertex. Because like I said, we're going to have to sort all of these vertices by the angle they are at from the light source so that we can ultimately create a realistic triangle fan. So this is just so we've got a structure called angled vertices with a vertice, an angle for that vertice, and the UV so that we can map our texture properly. Next, we've got a couple, honestly, not great, kind of annoying methods. I don't think this is optimized. This is basically because I'm using arrays throughout this entire script. That's in part because Unity uses arrays throughout all of their features, but also I just like using arrays. So you could definitely optimize my script by using linked lists or something similar, but I didn't worry about that. So I just have these two helper methods. This one adds items to an array, as you can see, and it returns the new array. So what it does, I'm going to explain it really quick, is it takes in an int array and takes in 3 items that you want to add to that int array, and it's a new int array with a length of the original length plus 3 because we're adding 3 items, does a deep copy of the original one into the new one, and then adds 3 items to it, and then returns that int array. It's very simple. You can go ahead and basically just copy it into your program, and I'm going to actually close it down just to get it out of the way because we're not going to be making any more changes to this. It is as it's going to be at the ending of the project. The same goes for the concatenate arrays script, and it's literally that. It just concatenates the first array with the second array. So it takes in a first one, and the second array creates a new array that is the length of both of them combined, copies the first one into the location in the first half of the new one, copies the second one into the second half of the new one, and then returns the new one. I'm sped through that really quickly because it's really not what this tutorial is about, but that's basically how it works, and I'm going to minimize it as well. We're going to use it once and not make any more changes to it. So now we're going to go into the awful mess that we've added to our update function or method. The first thing that we've added is right here, mesh.clear. So that basically clears all of the information we've currently got in the mesh. I believe that means getting rid of vertices, UVs, and everything like that. I do this because I've been told to. People online say that's a good practice if you're procedurally generating and repopulating the mesh. You go ahead and clear it. So that's what I do first of all inside the update. And then the next thing is this line of code right here. And basically what this is doing is it's creating an array of vector 3s that store all of the vertices for our game objects. So we have one thing that references to every single vertex. So first of all, it just takes the first scene object that we want and pulls its vertices from the mesh into this object's verts, obj verts, and then it scrolls through every other game object or scene object that we want to react with the light, and then concatenates onto that array using our little method up here, the vertices for that game object. So we're just ultimately at the ending of this line, we have an obj verts variable that is a vector 3 array of every vertice that we want to react with the light source. Now going on down here, you'll see these 3 lines, and they're just more initialization, basically. So first of all, you see this angled verts. You'll recognize that from the structure we made up here. And we're going to make an array of these structs. And initialize it. It's going to be empty starting out, but we're just going to initialize it to the length of the number of the vertices times 2. So the reason times 2 is because we are going to be shooting actually 2 rays per vertex, if you remember. We don't have to pass one to the actual vertex, just one slightly to the left and one slightly to the right. So that's going to be the number of vertices that are going to be in our total mesh, the number of vertices in the scene times 2. The next two lines are what we're actually going to ultimately be setting the vertices in the mesh and the UVs in the mesh to, and you'll see that later. And basically, they're both really the same thing as each other, just one's a vector 3 and one's a vector 2 because it's UV. And then what it is the same thing, objverts.length times 2, but there's a +1, and that +1 is because we want the first location in both of these to be the location of the actual light source. So we want this to be our first vertices so we can create that triangle fan I'm going to explain a little bit more on later. And then these two lines of code is just that, getting that point and setting it to the first location in verts and UVs. So how we get it is we do another matrix multiplication, but this time it's we're pulling it from the world and setting it to the local system for this light rays object. So we're getting our current object's position, and then we're doing the world to local matrix multiplication, and the local matrix that we're putting it in is this light rays for its transforms object. I hope that made sense. If not, it's okay. Just copy the code if you feel comfortable with that. So the UVs is really the same thing, except instead of a vector 3, we want a vector 2. So we can just take the same values we put into here and put them as a vector 2, just the x and the y, into the UV's position. So there we are. We've got our first vertex and our first UV. The next line of code is this right here, and this is just a way so that we can index as we go through these angled verts. If you think about all of our vertices to be in like a 2D array, for each object you've got an array, and for just going down, then this value keeps track of every time we go to a new tile. Even though I and J doesn't keep track of exactly how many vertices we've gone through, H will. So we look at this code and it's all the same thing as we've seen before. This is all the same thing as we've seen before. And incidentally, this is the exact same thing as we had before as well. To save you a little headache of trying to figure out if there's anything different, it's the exact same thing. The first change we have is this right here, this angle 1 and angle 2. So down here you'll notice, yes, we've been passing in the direction of in the direction from the current location to the vertice location. So it's like we already have an angle, but we don't. What we actually have is a vector 2 or a vector 3 if you wanted to of how that vector should be passing. But what we actually want is like a floating point value of an angle either in radians or degrees for us to be able to measure them in comparison to each other and know which and so that we can sort our vertices in an actual tangible way. That's what these lines of code do. And they're the most mathematic-y part of this code. I honestly can't remember exactly how atan works mathematically just because it's been a while since I've had that class. But basically what this is doing, mathf.atangent2, is finding the actual angle given these 2 points, the angle from the first one to the second one. And you'll see this line of code is basically the same thing as down here. If I line it up, you can see it's the same thing as this. The current vertex location y minus my location y, then minus the offset, and then we've got the plus offsets down here, and these are the y's and these are the x. Just one thing to notice is that the y in this function actually does come first, because I believe it's like y over x. So the y comes first, and then the x comes second. So don't get those mixed up like you've got down here where the x comes first and then the y is calculated. It's swapped, as you can see if I highlight these. So we've got our two angles for our two rays that we're casting. Again, this is the exact same thing as before, no need to change that. And then we come down here, populating our angled verts struct. Now this works with our h value that we had, so we can keep track of exactly where we are. This h times 2 and then h times 2 plus 1 is just because we want to populate, each time we go through this, two different locations, one after the other. You can kind of actually notice, for fun fact, that this is like the equation for even numbers and this is the equation for odd numbers, where h is some integer. That's because we first want to populate the even location, which starts out as 0, then the odd location, which is 1, and then 2, and then 3, and then 4, and then 5. And we go through that so we're not messing anything up there. So first of all, we're at 0 position, so this would be angled vert 0. And then what we populate into the vertex for this location in the struct is another world to local matrix. So we've got this hit point, which we calculated with our raycast up here. And again, hit points are in world location, world coordinate system. And we want it to be just like what we had up here. We want it to be in the light rays coordinate system when we actually go to pass these vertices into the mesh, the mesh's vertices. So we're just going to do a transform right here from the world to the local matrix and pass that into this value. Angle is easy. We've already calculated the angle up here, so we just set the angle to equal to angle 1. And then the UV is also easy because it's, again, the same thing as what we did up here. It's just going to be a vector 2 instead of a vector 3. Since we've already done the calculation up here and stored it in vert, we can just go back to that location and back to that vertice, take the x and take the y, and set the UV to a vector 2 of those two. This is basically the same thing. You just want to be careful with the things that are different. For instance, all 5 of these locations have a +1. So this location, this, and this, and this all have that +1. And then also we're doing hit 2 instead of hit 1. And then angle 2 instead of angle 1. Other than that, it's the exact same thing. And then after all of that, we increment h by 1 so that we're going to the next locations the next time around. Now, if we go back into Unity and run this, we're not actually going to see anything different. Nothing's changed. It's still behaving the exact same way as it was before, but we've just done a bunch of initialization because we haven't actually passed any values into this ray's object to manipulate its mesh. So that's what we're going to do next. And this is actually, don't worry, this is a lot less code than we have done before. We've gotten through the majority of the code. But we still have a little ways to go now. So I'm going to paste that in there, and I'm going to explain this. So we've got these structures, and we've got a vertice and a UV paired with an angle, which is great, because now we can actually sort this, this object. Sort the vertices. And before I do sort the vertices, I want to explain a little bit more in detail what a triangle fan is so that this makes sense. So I'm going to actually come in here and undo what I did beforehand. So I get rid of those error messages, and I'm going to hit play once the script is compiled. All right, so what a triangle fan is, for the basic definition of it, is a triangle fan is a bunch of triangles, all of which that share one common point, which is in the center of all the triangles, and then each triangle's 2 other points is shared by some other triangle. So basically, if we saw this as one triangle, we want to create a triangle between point 0, point 1, and point 2. The next triangle would be between 0, point 2, and point 3, the next 0, point 3, and point 4, and so on and so forth, until we've done the entire thing, and then the last triangle would be 0, point, final point, and then point 1 again to close it off and not give it like a slice of pizza is missing. So as you can see, it has to be in that order. We can't just do point 1 and point 5, or that'll create a weird triangle like this and it'll look awful. And the problem, to make matters worse, all of these vertices are specified in no particular order. If I go to the light, I've just dragged and dropped these in randomly, and there's no guarantee that the vertices would be in any order based on where the light currently is. So that's why we're sorting all of this by angle, because we want to make sure that our triangle fan actually is properly created, properly generated. So let me go back into the script, and I'm going to paste that code back in. And now I'm going to explain it. So now that we've got all of those angles and the vertices and the UVs all paired up, we can actually sort it. And it's by this little magical piece of code that C# is so nice to give us. I don't know exactly how it works under the hood, but the basic way to operate this system.array.sort method is the first thing you pass in is what you want, is the array that you want to be sorted. And then this delegate is like, if we suppose we have angled verts 1 and angled verts 2, we want to compare the value in angle for both of them, and then sort this entire array based on those angles. So that's what's happening here. It's a bit of computer science magic. I honestly just went onto like the C# forum and copy and pasted this, and then modified it to fit my needs. So that's kind of how it works. Not going to go into great detail there. And now, once this is done, our angled verts struct array is completely sorted, and we can actually start to pass those values into the completed process. So we're going to just do a simple for loop, which is the length of this structure array, and then pass those values in verts and UVs, since we don't have to worry about angle anymore now that it's served its purpose for sorting. Pass the vertices and the UVs into the verts and UVs array, +1, because remember that primary value is the vertice at point 0 with a UV at the center. And so we just pass those values with an offset of 1. And once we've done that, our vertices are actually complete. Our vertices array is actually exactly how we want it, and we can just pass verts straight into the mesh itself, and so update the actual vertices for the actual mesh. The UVs are a little bit more complicated just because how UVs are set up, they're not based off of the center of an object, but they're based off of the bottom left hand of the object, and they scale from 0 to 1. So what we're going to do is we're going to set that offset a little bit back into the center so that the light is actually emanating when we put a texture from the center of the object. So we're just going to do another for loop for the UVs.length, and then set each UVs to what it was before, plus 0.5 on both X and Y. And once we've done that, we've got the offset problem fixed, and we can pass our UVs straight into the mesh's UVs like we did with the vertices. Now, all that's left is the triangles. And so to explain that a bit more, I'm actually going to remove this bit of code so it's not a distraction. What we're ultimately going to want to do is the same thing we've done for the vertices and the UVs. We want to pass an array into the triangles. And this array is going to be an array of ints, or integers. Ultimately, what it's going to be, an array of integers that is like index locations referring to the vertices. So a 0 in this would be referring to the first vertice in the vertex array. And it's also going to be the length of the vertices times 3, because each triangle is made up of, obviously, 3 points. And how Unity reads this triangle array is it takes the first 3 points and then creates a triangle based off of those points, and then takes the next 3 points in the triangles array, looks at them as indexes to the vertices, and makes another triangle, and so on and so forth. So if it looks at the first ones and sees a 0, 1, and 2, then it will take the 0th, the first, and the second from the vertices and make a triangle there. Now, what we ultimately want in here is every group of 3 index locations in the triangles array, we want it to start with 0. So like say 0, 1, 2, 0, 2, 3, 0, 3, 4. And that will create our triangles in the triangle fan format, so that each triangle is, as I described earlier, sharing a common point among all of them, and then each one's 2 other points is shared commonly among 2 other points. So now I've explained that a little bit more, and if you want more information on how triangle fans are formed, there's plenty of information out there for you to understand it a bit more. But now that I've explained it just enough for it to be helpful for our situation, I'm going to put that code back in here. What we're first going to do is we're going to initialize that triangle's int array to our first location that we want, our first triangle we want to make, which is going to be, as I described before, 0, 1, and then vert's length -1, so the last vertice. This will solve that slice of pizza issue I mentioned earlier, to make sure that we don't create everything and then just leave that last place open. We're just going to do this first and foremost, 0 combined with the first vertex and the last vertex, just to fill that slot in. If you don't really understand what I mean, you could kind of remove this and you'll see like a slice of pizza taken out of the triangle fan in the completed project. And then we've got this line of code, and if you've been sort of meandering your eyes down to here, you'll notice I've got this sort of backwards, where I'm decrementing this for loop instead of incrementing. I isn't equal to 0, it's equal to verts.length minus 1, and then we're testing while I is greater than 0, I decrement. This is because of the normals of triangles and how they're determined and calculated through Unity. Now, I'm not going to worry in great depth about this if you haven't dealt with generating triangles. I don't expect you'll be dealing with this huge amount in Unity, but basically how the vertexes are combined determines the normal of the triangle. And if you're behind the normal of the triangle, you don't see it at all. You may notice this in your time in Unity when you go into an object or you go underneath a two-dimensional plane, you can't see anything. It's because the normal is facing the other direction, and so it doesn't get rendered when you're not facing it. How that all gets determined, why this is important for us, is based on how the vertices actually get passed and combined together. And what I found is if I do it incrementing, like an incremental for loop, they're all facing directly away from the camera. If I just do a decrement, and so I'm going backwards through the vertices, then it faces towards the camera and it all works great. So if you're in your game, it's all facing backwards when you do this, just make this incremental and make this +1, and it should work fine for you. And so each time we want to increment, we want to add 3 items to the end of the array, as I described in this helper function we made earlier in the top of the code. And so we're going to add to triangles 0, we're always adding 0 in that first location, the current I, and then I minus 1. And next time, I is going to be equal to what I minus 1 was beforehand, and so on and so forth until I minus 1 is down to 1. And then once we've done all of that, we've created our triangle fan perfectly, and now we can just pass this triangles array into our mesh and complete the mesh triangle fan. Now, if we come back into here, we should be done with our script. And if we test it, we can determine that for sure. And it indeed looks to be working. You can see that the line of sight is great. It's kind of ironic that anything in the light is black and everything else is actually in light, but it's working. And I said, I don't know if you can see in the video, if you're following along, you may notice when you walk in an area like this, you see some jittering. That can be modified by changing your offset and modifying it specifically for how you need in your scene. For me, it's working fine. However, obviously, we don't want the light to just be black and we don't want it going everywhere. Thankfully, we've already set up our UVs properly, so this is going to be very easy to implement. I'm just going to hit play again to pause it. And as you can see, what I've got right here is I've got this light source texture that I just created in GIMP. You could create it in Photoshop or whatever. I'm not going to bother explaining this for the same reason I didn't go into Blender and make changes there. But basically, or I'm not going to explain how to make this, but basically it's just a transparent PNG with sort of this weird sort of spray can stuff in the center to make sort of a light emanating. And so that's what our light source is going to be. So to make that work, we're going to create a new material. And I'm just going to call this light source. And then what we're going to want to do is we're going to change the shader type to unlit transparent. Transparent because there is a transparent backward to our light source and we want that. And unlit because this is just a good practice for any object or texture that is the lighting. You don't want light to affect it. So unlit, transparent, and then just drag whatever texture you're using, if it's the texture I have in here or your own, into the texture slot in the shader. And then when we go to this raise object, not the light object, remember that's an empty object, to the raise object, we're just going to drag our materials, our new material to this element 0 position, and we've got our light. Now, some people may implement into their script another variable that would change the size of the light. And if you were creating a specific shader instead of like a texture, that may make sense. But in my case, honestly, it just makes sense to scale this up to be the size that I want. So scaling the entire light object up. So I think that's pretty good right there. So I'm going to go ahead and play. And you can see it's working great. We've got the fall off and everything, and the even though the mesh is changing different shapes, it's maintaining its UVs perfectly. And obviously at this point we could remove these lines. What I did the first time around is I had like a checkbox over here that would remove the lines or keep the lines in there. But in the scene you can't see them at all. And then just for flair's sake, I'm going to add another object, another PNG to this light source. And I'm going to set its position to 0 based on the light. I'm going to set its layer to something higher than the light, and then scale it up to make it look a little better. Show what's actually creating the light. And if we drag this around, there we are. You'll notice that it keeps working like that. Now, as I've mentioned at the beginning of the video, there's a lot of different ways to optimize this, and also, as I mentioned before, those edges are kind of ugly. That's just because our collision was extremely simplistic, and that could be modified on your own. But that's the basic idea of how it works. Again, please let me know how this can be modified. Feel free to be brutal. I know it can be made better, and I want to see how. And thank you so much for sticking to the end of this video, and I hope it really helps you guys with your games, adding your 2D lighting without having to buy expensive software or using someone's own assets. Thank you again for watching this, and I hope you enjoy.